now that we already understand how to determine binding energy, let's move on to talk about binding energy per nucleon. So binding energy per nucleon is a physical quantity that can be determined by taking the binding energy EB divided by the number of nucleons in the nucleus A. Okay, A over here can also be called as mass number in chemistry, but basically it's just the number of protons plus the number of neutrons. So binding energy per nucleon is an important measure of how tightly a nucleus is bound. So generally, if you have a tightly bound nucleus, you have a great binding energy per nucleon. If you have a loosely bound nucleus, you have a low binding energy per nucleon. So this binding energy per nucleon here represents a measure of stability actually. So if you think about it, it sort of makes sense, because if you have a tightly bound nucleus, that means that you have a high binding energy per nucleon, right? High binding energy per nucleon means by the nucleus itself will have a great binding energy. So if it has a great binding energy, according to the definition of binding energy, it means by it will require great amount of energy used in order to break apart the nucleus into its completely separated constituents. So if you need a great amount of energy to break apart into completely separated constituents, it means by that process is quite unlikely to happen. Because if you need a lot of energy to make it happen, that kind of energy you cannot obtain it that easily. So that means by that kind of process is very unlikely to happen. So if the process of breaking up is very unlikely to happen, it is equivalent to saying that that nucleus itself is very stable. So therefore, if you have a high binding energy per nucleon, it means by you have the nucleus itself will have a high binding energy. So if the nucleus has a high binding energy, the breaking up process is very unlikely to happen. It has a great stability. On the other hand, if you talk about loosely bound nucleus, you have a low binding energy per nucleon. So low binding energy per nucleon means by generally for that nucleus, you have a low binding energy. So if it has a low binding energy, it means by it requires a less amount of energy in order to break up the nucleus into completely separated constituents. If it requires less energy, that amount of energy is more easily obtainable. Okay, you are able to achieve the amount of energy needed more easily. So if it's more easily, it's more likely to happen. That means the breaking up process is more likely to happen. It means by the nucleus itself is less stable. Okay, so even though binding energy per nucleon here, it's a value, but it represents stability. Okay, if you think about its definition for binding energy per nucleon, right? Binding energy per nucleon, the definition is the amount of energy required to remove one nucleon from the nucleus. Okay, if I want to extract just one single nucleon from a nucleus, how much binding energy do I need? Okay, so how much energy do I need? So if you think about it, it makes sense. If you have a high binding energy per nucleon, it means you take a lot of energy, you require a lot of energy to extract just one single nucleon from the nucleus. So if it's very difficult to extract it, that means by the nucleus itself is very stable. Okay, so that's generally the idea of binding energy per nucleon. But when we talk about this value, right, to remove one nucleon from the nucleus, right, and that process, right, it's not physically doable kind of process. You cannot just take one nucleon from the nucleus. It's not that easy. Okay, this kind of process we don't really do it. We don't have this kind of process to take out one nucleon from a nucleus, but it is just an idea to represent how difficult is it to break apart the nucleus. Okay, it does not physically happen, the process of taking apart one nucleon from the nucleus. That process doesn't physically happen, but this kind of value here is sort of represent how difficult is it to break apart the nucleus. So then, because this value itself represents how difficult is it to break apart the nucleus, we can equivalent it to the measure of stability. Okay, so usually we as physicists, we usually sketch a graph, or we will plot this kind of graph to show how does the binding energy per nucleon varies according to the number of nucleons in nucleus. Okay, so over here you have your number of nucleons, which is protons and neutrons add up together. So this represents the number of nucleons that you have in the nucleus, and here it represents the EB over A. For the EB over A for these different kinds of elements and isotopes, what you get for their binding energy per nucleon. Okay, overall you should be able to observe the trend and describe the trend, and we will try to explain why the trend looks like this. Okay, overall the trend, you can see that there's a spike in the average binding energy per nucleon. There's a sharp increase in the binding energy per nucleon until near this region over here where A is around 30. From 0 to A around 30, right, there's a sharp increase in the binding energy per nucleon. But even though it's a very sharp increase in binding energy per nucleon, you have some unusual cases over here which you can observe to be helium-4, carbon-12, and oxygen-16. You can see that these three nucleus here doesn't really follow the general upward trend, because there's a significantly high average binding energy per nucleon of these three nuclei compared to their neighbors. Okay, so these three nuclei are special in some sense, which we'll explain later. But generally, you should observe a sharp increase in the average binding energy per nucleon, but with three peaks or three unusually high binding energy per nucleon occurred for He4, carbon-12, and also oxygen-16. Okay, then after that, when it enters a range of around 30 to 90 number of nucleons, from 30 to 90, right, you can see that generally it gets stable, or it sort of plateau around a certain value which is in between 8 and 9 MeV. It plateaus around this region from 30 to 90. Means that generally here the nuclei from 30 to 90 generally, right, they are about the same kind of average binding energy per nucleon. But from 90 onwards, right, you can see that the value, the average energy per nucleon, sort of tapers off. You slowly decrease, not as sharp as the increase before this. You slowly decrease as you approach the uranium. Okay, of course you have other nuclei which have a greater number of nucleons compared to uranium, but those are not shown on this graph over here, because for those nuclei which are very, very large, larger than uranium, usually they cannot be formed in nature. Or you can say that even though they are formed in nature, right, they will spontaneously decay to lighter nuclei. So it means by that kind of nucleus which are larger than uranium, right, they cannot be stable and exist in nature just like that. Okay, once it's formed, right, you immediately get very unstable, then immediately they will break apart into smaller, lighter nuclei. So in that case, it's very difficult, or I think it's impossible to observe in nature. So you have to create it synthetically in order to observe it. But if you try to find it in nature, you will not be able to find these kind of nuclei which are heavier than the uranium. Okay, so we are stopping at uranium over here. Okay, so in order to understand why is it a sharp increase, a plateau followed by a tapered off as it grows, as it goes further, we have to understand what kind of interaction is happening inside here. Okay, we have studied in the first video of this section that how nucleus binds together depends on nuclear force. Okay, strong nuclear force. Even though protons and protons, they are supposed to repel each other, but because of the existence of strong nuclear force or strong force, it allows those protons and neutrons to be able to bind together into a formation of nucleus. But we have to understand the properties of strong nuclear force very clearly. So strong nuclear force, right, it does not depend on charge. So that means if you bind together a proton and a proton using strong force, it is the same as binding a neutron and a neutron together with strong force, or a neutron and a proton with strong force. Binding no matter protons or neutrons, if you're talking about strong force interaction, they don't differentiate whether you are protons and neutrons. They bind it the same way. Okay, so the strength of the strong force will be the same either. Okay. The second properties of strong nuclear force is that it only happens in a very, very short range, which is on the order of 10 to the power negative 15 meters, which is about Fermi. Okay, so for the strong force can only be activated if you are in that kind of very, very short range. Once you go slightly further away than that, when you go further than 10 to the power negative 15 meter away from each other, the strong nuclear force will decrease very drastically. So it means when you are near together on the order of 10 to the power negative 50 meter, the strong force will be very strong. But once you go outside this range, right, the strong force will decrease very drastically. Then the strong force will become very, very weak if you are out of range. Okay, so that causes protons and neutrons in the nucleus, right, when they are trying to bind to each other, right, if the nucleus is too big, right, they are only able to bind properly using strong force with their neighbors only. Okay, they are only able to bind with the nucleons in the immediate vicinities. So if the nucleus is this big, right, the neutrons over here might be able to bind to the protons and neutrons around this region, but they are not able to bind to the protons and neutrons which are on the far side of the nucleus. So you can think of the neighbors hold on to the neighbors. So they are not holding on to the protons and neutrons on the far side of the nucleus, they are only able to hold on to their neighbors only. But this is very important to explain why the graph causes a increase followed by a decrease. Okay, so let's explain the idea over here. So the idea over here is your nucleus is still very small. Okay, all the nuclei over here are very generally relatively small. So the strong force, they are able to cover the whole nucleus. Okay, the whole nucleus is still within this size over here. So that means by if you add on the protons, if you add on the neutrons around this region over here, right, the strong force will be able to interact between one neutron on the left hand side and one proton or neutron on the right hand side. They are still able to attract each other even though they are on the far side of the nucleus, because the nucleus is still very small. So all the neutrons and protons over here are able to attract all the neutrons and protons on the other side using strong force. Because the nucleus is still very small, they are still able to attract each other using strong force. That's why, as you see, even though we add on the number of nucleons in these nuclei over here, the number of nucleons increase, but the strong force is still able to interact with all the other nucleons in the nuclei. So they are still able to grab onto it using strong force. So it is still increased in stability at this range over here. Okay, but the problem is when you enter this range over here, your nucleus has already reached a certain size already. Okay, the nucleus reached the certain size which is near the limit of what the strong force can interact already. So you already reached a size in which you are near the end of things already, where left hand side can still interact with right hand side, the bottom can still interact with top of the nucleus, but that's about it already. If you go larger than that, which is this range over here, your nucleus will be too big in the sense that the nucleons on the left hand side cannot really attract the nucleons on the right hand side only. What they can do is only attract the few nucleons that are near the nucleon itself. Okay, they can only attract to their neighbors only, but they are not able to effectively attract all the other protons and neutrons on the other side of the nucleus. So when that happens, right, at the same time, your number of nucleons increase, means by the number of protons that you have also increase as well. So when you're in this region here, what happens is the strong force doesn't really increase anymore. Okay, even though you add on protons and neutrons, the strong force that interacts in this nucleus can never really increase anymore, because you already reached the limit already. Even though you increase the number of protons and neutrons, you will not cause a strong force. Instead, what happens is you make the size of the nucleus larger. They are still not able to interact with the far side, they are only able to interact with the neighbors only. But at the same time, you know that the increase in nucleons means by the increase in protons as well. So if your protons gets more and more and more, what happens is the protons should be repelling each other, right? So the repulsion force will keep increasing, because repulsion, you know, is kq over r squared. So even though it extends to infinity, right, even though your r goes to infinity, only your force can go to 0. So that means that even though the distance is quite far away, they are still able to repel each other quite strongly. Okay, strong force, right, when you go out of range, right, immediately it drops very drastically. But when we talk about repulsion force, the electrostatic repulsion force, it doesn't drop off that drastically. So even though you are far apart, they are still repelling each other quite relatively strongly. So what am I trying to say here is the strong force never really increase anymore when you reach this region over here. You add on nucleons, the strong force doesn't really increase, but the problem is the the increase in protons causes the repulsion force to gradually increase. So the strong force never really increased, but the electrostatic repulsion keep increasing. So in that case, the repulsion will slowly overcome the strong force. The repulsion will slowly get stronger and stronger, comparable to the strong force already. So now because the repulsion is more and more significant, right, it will try to push each other apart. So it means by they cannot form a really stable nucleus anymore. So the stability of the nucleus will decrease as you go along this line over here. As you get larger and larger, electrostatic repulsion will eventually overcome the strong force. So the nuclei over here get less and less stable, more easy to break apart because the repulsion force is now much stronger. Okay, so that generally explains the trend. Why is it increasing initially? It's because adding of protons or neutrons still causes the strong force to increase, because still you're within the range where strong force can interact. Okay, but as you enter this region from 30 to 90, the strong force is approaching its limit already. So adding more neutrons and protons will not generally cause an increase in strong force, but at the same time it is relatively stable because the electrostatic repulsion is still not so strong yet. But as you go above 90 and above, the strong force never really increase, even though it add on protons and neutrons. But the problem is the increase in protons causes generally more electrostatic repulsion. So it gets weaker and weaker in terms of stability. Therefore, it has a lower and lower average binding energy per nucleon. Okay, so it is these two factors over here that generally explain this trend over here. So the idea is initially F strong is much greater than F electrostatic, but as you go further away, the F electrostatic will generally try to overcome the strong force, causing it to be weaker. Okay, the last point over here favors binding of pairs P and N and P and P, proton and neutron and neutron, and proton with opposite spin. This one is to explain why you have this unusual peak over here for helium-4, carbon-12, and oxygen-16. These peaks here are unusual because it causes this increasing trend to be not smooth, right? So it should be a very smooth curve, but you can see three unusual spikes over here. So these three unusual spikes, right, people usually call it as the doubly magic. Doubly magic. Okay, you can read about it in Wikipedia maybe, but the idea is for this kind of nucleus over here, this kind of nuclei over here, what do is they form pairs of opposite spins. If you look at helium-4 is 2 protons, 2 neutrons. So protons and neutrons, right, they are fermions. Okay, don't need to worry about what is it. So basically fermions, they have two types of spin. One is they have two opposite spins. You usually call it as up spin and down spin. If you talk about it in chemistry, when you talk about, I think, Pauli exclusion principle, you learn that electrons can have up spin and down spin, right? So it's a similar idea over here. Protons and neutrons, they also have opposite spins as well. They have up spins and down spins. So right now, if you are talking about helium-4, there's 2 protons, 2 neutrons, right? So the 2 protons will be opposite in spin, the 2 neutrons will be opposite in spin. So because they are pairs of opposite spin, strong nuclear force will favor the binding of them together. So that's why the binding force will be very strong, the strong nuclear force will be very strong. So it causes this spike in the average binding energy per nucleon for this helium-4 over here. The same idea is carried along for carbon-12 and oxygen-16. This one is 6 protons, 6 neutrons. So if you think about it, they can form, there's 6 protons, right? They can form pairs of opposite spins because it's even number. Then the neutrons also form pairs of opposite spin as well. There's 6 neutrons. So oxygen also similar thing, 8 protons and 8 neutrons. So they can form pairs of opposite spins. So from there, because they have these kind of pairs of opposite spins, this kind of binding is favored, causing them to have unusually higher binding energy per nucleon compared to their neighboring nuclei. So that explains the 3 spikes, the 3 peaks that you have see here. Okay, so there's a combination of factors that we need to understand in order to explain this graph over here. But I think in your syllabus, generally, if you're able to explain the general trend that you see, which is a sharp increase until A is around 30, then it plateaus around 30 to 90, followed by a tapered off kind of curve from 90 onwards. You're able to describe the trend and you're able to sort of understand it's a competition between the strong nuclear force and the electrostatic repulsion. I think that generally is enough for us to fulfill the requirement of this syllabus over here. Okay, so that's it for binding energy per nucleon. Thank you very much.